We saw the algorithm for quantum Fourier transform last time. This was on the lines of discrete Fourier transform, which was supposed to make the Fourier transform over group Zn happen. The quantum version of this was called QFT. If I have to be precise, I would say that the state J was moved to this state. We will remember this. For any basis state, this is what a QFT does. Now, the next subroutine, which is also very useful in quantum computing, is called phase estimation. I need to introduce the problem first, but let's talk about unitary operators. You have seen them a lot. Let's see what you remember. A matrix U is called unitary if UU dagger is called identity. These were a subclass of normal matrices. We have studied them thoroughly. Specifically, remember that for normal operators, we can always take matrix equations and in some sense write those equations in terms of eigenvalues. This is a short informal proof, but this can be formalized. So for a unitary operator, any eigenvalue should satisfy this equation. Another way to say it is that the absolute value of lambda is 1. Remember, lambda is a complex number. A unitary operator need not be Hermitian, so lambda need not be real, can be complex, but we definitely know is that its absolute value is equal to 1. Now, any complex number can be written as r to the power ei theta. In terms of radial coordinates, since the absolute value is 1, this implies that any lambda I is e to the I. Definitely say this for every eigenvalue of a unitary operator. Let's do some normalization and say that for a u, if ui is equal to lambda ui, that means ui is a normalized eigenvector, then every lambda I corresponds to some eigenvalue which is of this form, e to the power 2 pi I theta. Notice that there is not much difference here. I have absorbed a factor of 2 pi in the definition of theta. That should not trouble you. Keeping it like this, I can say that theta is the eigenphase of the eigenvalue lambda I or eigenvector ui. These three form a triplet. This is the eigenvalue, this is the eigenvector, and theta is called the eigenphase. We will be worried about eigenphase, and this is how eigenvalues and eigenphases are related. There is one-to-one correspondence between them. After this introduction, we can talk about the problem of phase estimation. You can kind of guess we want to estimate theta, but under some conditions. So let me say it slightly more formally. If we know how to perform unitary, or let's say slightly more generally, if I can perform u to the power k controlled operations, this is one condition, and we have access to an eigenvector. When I say access to an eigenvector, I mean as a state. So I can prepare state ui where ui is an eigenvector. In that case, then quantum computer can find the eigenphase. We have to be slightly formal here, we can find eigenphase up to the required precision. Let me specify what do I mean by required precision. Notice that theta can be assumed to be less than 1. In other words, I can say that theta is 0.j1, j2, jk. Reason being, remember, we talked about eigenphase like this. That means any integer multiple of e to the 2 pi I is 1. That means I can only worry about the part which is less than 1. So I can say that my theta looks like this. This will be the binary expansion of theta after the decimal value. In general, I can say that my problem is to find theta up to k decimal places. In this case, again, what are we given? Control u to the 2 to the L. We can apply those operators, and we can also use the state u, which is the eigenvector for theta. Given these two things, we can figure out theta up to whatever precision. Let's say first k digits of theta. Let's say we are interested in that. To show this algorithm, let me first make two assumptions. I will get rid of these later. This will simplify the description of the algorithm. What are the two assumptions? First, I will just say that the expansion of theta has only k digits. That is kind of a simplification. In general, it could have infinite digits after decimal, but let's keep it simple. Let's assume that theta is just this. This is the complete expansion of theta. We will get rid of this assumption later. You can think of the reason why we can get rid of it, because by linearity we will get something very, very close to it if we just approximate the procedure. That will be the idea. But let's see, we will say something more of how to get rid of this. Other thing is that we assume that we had control to the u to the power L, but I will assume I have the access of u to the power L for all L less than 2 to the k. This seems like a more general thing, that I have u to the power L, not just the powers of 2, but using control u to the power L, I can simulate these. And this again will be done later. To start with, let's say we have these two assumptions. My expansion just stops after k digits, and I have u to the L for all L, not just for the powers of 2. Given this, how can we do phase estimation? The process is not very difficult. Let's see. It will be very, very similar things to what we have been doing. Just we will have this extra register. Remember, we have the access to the eigenvector. So let's take two registers. One is 0, one is u. This is going to be k qubits. This is the required amount of precision for the algorithm. Now it is easy to convert the first part into an equal superposition. You can do it using Hadamard. You can do it using Fourier transform. This is not hard. This will be the final state. This should not surprise you. This didn't even use the state. This gives you an equal superposition on the first part of the state. So okay, so let me just call that this is Hadamard. Now I want to apply u to the power L when the first register is. The claim is that I can get to this state. Let's say that I make my indices to go from 0 to the power k minus 1. This won't change anything instead of 1 to the power k, because I've assumed that I have e to the power L for less than 2 to the k. Why can I do it? The reason is, classically, it can be done. If I can apply u to the power L, and if the information in the first register is L, then I can do this classically. I can look at L, and depending on that, I can apply the correct unit. If I can do it classically, then I can do it in the quantum way also. This can be done. Again, we will see an explicit circuit, and you will see how it has to be done. Now, what is the action of u to the power L? It should give you the corresponding phase. 1u gives a factor of 2 pi I theta, then L of them will give this much phase. This is just calculation. The reason being, uu is e to the 2 pi I theta u. So you can see what u does. It should be clear to you what u to the power L will do. Notice this state, it is actually not entangled. The second part is always u. I can write that state separately. The first part of state is this, and then the second part is u. Now I want you to look at this part. Focus on this and tell me, do you recognize this state? If you take some time and if you were careful enough, you will realize that this is the Fourier transform of 2 to the k times theta. That is J1 Jk. This is the state which we wanted. So now what we will do? We will apply inverse Fourier transform. And measuring this will give us the answer. At this point, you might have a question. What do you mean by inverse Fourier transform? We already saw how to apply Fourier transform. But that's okay. Every gate in Fourier transform can be inverted. So we can invert the circuit of Fourier transform. And that will give us an ability to apply inverse Fourier transform. Other way would be, you actually find out the matrix for inverse Fourier transform, and using the same tricks as Fourier transform, you can apply inverse Fourier transform. It should not be hard for you to see that we can apply IFT using the Fourier transform. This completes the description of the algorithm. A very, very simple algorithm which takes the complete superposition, then applies the unitary according to the first register, and then some bit of calculations. These show that our first part of the register becomes a Fourier transform of the quantity we need. We needed theta, or to the power k times theta, and the first register is the Fourier transform of that quantity. Let's take the inverse Fourier transform. That finishes the proof of phase estimation. Not really. Remember, we had two assumptions. What was the first assumption? The first assumption said we have the ability to apply u to the power L instead of controlled u to the power I. Here I will vary from 0 to k minus 1 here, L will vary from L to 2 to the power k. How can we replace these? The simple idea is binary expansion. If I want to, for example, I want to simulate U cube. Let's say these are the qubits. This is U. These are the states which will represent L. Then I will take controlled operation from here. This is the least significant bit, and then similarly L1, and I will apply the unitary here. In that case, this will be U square, this will be U. And now we know that for the binary expansion of 3, L0 and L1 both are going to be exactly 1. That means U times U square equal to U cube will be applied. Let's take slightly different example. Let's say U to the power 5. This is in some sense in the binary expansion U101. Again, I will have L0, L1 and L2. I will use them to apply U, U square and U to the power 4. When L is equal to 5, then U will be applied. Remember 101. U will be applied and U to the power 4 is applied. On this state U, I get to apply this and this. What I get here is U to the power 5 times U. This shows that just by this binary expansion and controlled power of U's, or 2 powers of U's, I can apply any U to the power L for this. I can actually make a simple circuit. You can see that this particular circuit will work. You can easily verify that this circuit will work. Let's say these are the first k qubits, first register, and this is U. Now this is where I can use Hadamard or Fourier transform up to U. But then using this k qubits, each of them I use to apply a power of U. Like this. I should not say U to the k, I should say U to the power 4. And this will be U to the power 2 to the power k. Notice how they are controlled. This means if you just calculate this explicitly, you will see that here you will get 0 plus on the second you will get 0 on this you will get theta 1. Obviously omega here is the nth root of unity. I should probably make it correct. W should be e to the 2 pi I. This is the exact product multiplicative form which we saw for Fourier transforms. This is the exact product form for Fourier transform. And this I take it and apply inverse Fourier transform. That will give me theta. Notice that the last state is unentangled, it remains. This allows us to use controlled powers of 2 instead of u to the power L. So u to the power L can be replaced with controlled u to the power 2 to the power I. That gets rid of the first assumption. What about the second assumption? Do you remember what was the second assumption? We said that we can assume theta to be of the special form. That theta was some phase only up to g to the k. In general, theta will be like this. This was the assumed one. This is the general case. And then we will ask, give us the first k bits. It turns out that, remember, we did the phase estimation with k qubits. If we do the phase estimation with slightly more qubits, this is, so suppose we want epsilon error or probability, error in probability, then we take slightly more qubits, not k, but k plus f epsilon. Then we will get first k bits of theta with probability more than 1 minus epsilon. Notice that this does not depend on k. This is just what you want as the epsilon parameter. I will not expand upon this. If you are interested, you can consult the book of but it seems believable. If we do this operation for slightly more qubits, if we try to guess j1 to jk plus f epsilon, the first k bits will be correct with very, very high probability. This is in some sense the linearity of inverse Fourier transform, but let's not worry about it. If you are interested, look at this book. This shows that our two assumptions can be removed. And now you know that if you are given controlled e to the power I and an eigenvector, we can guess or we can estimate the corresponding eigenphase. Before I finish, there is another interesting thing I would like to tell. It's a simple thing, but something which we don't care about, or we forget to look at the details. I said that I have the access for eigenvector u, but that's not going to happen most of the time. It's not clear that I can get eigenvector u easily in most of the cases. What happens if I apply phase estimation on some random vector w? This might not be a eigenvector. What will be the result there? You can pause the video and think of what could be the answer here. The answer is hidden in linearity. Notice that w can be written as alpha ui for some alphas, because the eigenvectors of u will form an orthonormal basis. They will form an orthonormal basis. Hence, any eigenvector, or sorry, any vector can be written like this. In that case, if I apply phase estimation, then I will get theta I with probability alpha square. This is just the superposition. This is how it should act. And this property, this seemingly clear property, will be very useful in show cell.